everyone. Welcome to the Data Lake Summit 2020. Thank you, Qbol, and the sponsors for inviting me for this talk on multi-tenant data lakes. My name is Pravanjan Choudhury. I'm the CTO of Capillary Technologies. Capillary Technologies is a multi-tenant SaaS platform on the cloud. We provide customer relationship management, targeting platforms, and insights for our customers. We serve about 250 plus customers across the globe. The topic of today's discussion is multi-tenant data lakes and how they differ from single-tenant data lakes, and what are the added layers of complexities and how we have managed to navigate those. So, topic of today's discussion is 5 reasons why multi-tenant data lake is a different ballgame. As I mentioned, we'll go through Capillary's journey of building this multi-tenant data lake and what have been our key learnings on the process, and how this adds to an added layer of complexity to a single tenant data lakes in general. Now, who this talk is relevant for? So this talk is relevant for system designers, developers, product managers, analysts who are trying to build a multi-tenant data lakes. In Capillary's context, it's a 10-member team. We call it Essential Insights team that builds out this data lake, responsible for managing this data lake, and also provides APIs for rest of the engineering teams to build products on top of this data lake. And this talk is relevant also for building a modern domain-centric data lake. In our case, it is retail and consumer brands, but in your case, it could be some other domain. Talk could be relevant for you. Our whole data lake is built on Apache Spark, and the third point is it is relevant if it is a multi-tenant environment. We serve about 250 plus enterprise customers on our product suite. And including a set of diverse stakeholders. So close to about 10K stakeholders is what participate in the data lake in some form or the other. They might be interacting with the data lake through our products and services, or they could be working on the extensions of the data lake and working on a very, very standard tool sets on top of our data lake as well. Now get to the Capillary's journey on building this data lake. Like any other platform which is built on for the last 10 years or so, it has evolved through the data lake concepts. Now to understand Capillary, we essentially integrate with retailers and consumer brands across the globe. We integrate to their point of sale system, their back office, capture all kind of omni-channel data sets that those customers have, bring into our data lake, and there are several products and services which powers this data lake. When we started, back in 2009, 2010, the first version of the data warehouse that we launched is close to 2011. It was completely built on data warehouse concepts. So there was sharded MySQL servers, which were serving the data lake, and there were a bunch of ETL scripts that used to take the data and then put it inside the data lake. They served for us for about good couple of years, but then soon we hit the limit where we had to scale up the data lake. Right. So if you look at the modern data lake evolution concept, the first set of tools that came in were primarily the Hadoop and Hive ecosystems, which tried to optimize the batch or the ETL workloads. We adopted that. In 2014, we had the ETL flow of our data lake completely moved to Hive and HBase, where we could serve or process rather a bunch of our tenants and having very large data sets to our data lake. But at the same time, the data serving layer still resided on the MySQL sharded databases, where we, each shard used to contain set of tenants, and those tenants and the serving layer used to be based out of those MySQL layers. 2018 is when we launched the version 3 of the data warehouse, which is built on completely on Apache Spark, both on the ETL layer as well as on the serving layer. We also added a bunch of additional capabilities to our product, and I will talk a little more about how those products grew along with the data lake in this duration as well. Come 2020, this is the current state of our data lake. We have about 250 plus enterprise customers, several thousands of small customers as well, SMB customers as well. We have close to about 150 terabytes of data lake, which is powered by the data lake. Then there are thousands of KPIs which are defined on the platform. There are about 60K point of sales that are connected to the data lake, as well as close to about 10K users or stakeholders on the platform. So that's the current state of the data lake. And this talk will going to talk more about how we have built this multi-tenant data lake and the complexities that are arises for serving all these large customers. So let's say you're building a single tenant data lake versus a multi-tenant data lake. There are some minor differences between how you approach the problem. If you're building it for a single tenant data lake for a particular customer or a particular company, you're essentially looking at a bunch of code that can transform the data from the source systems to the target systems, and then have in a way. Optimize that serving layer as well. But the single tenant data lake is in some sense is a little easier problem in a way that there are defined set of guidelines on the internet which talks about how to build this data lake out. There are fewer literature on multi-tenant data lake, and that's something this talk is going to focus on about. Now, in Capillary's multi-tenant data lake platform, here are a few aspects which basically adds to the complexity of the data lake. We have products which we call internally as Insights Plus, then our targeting platform, our customer segmentation platform, and then a recommendation and personalization and various AI-based solutions as well running on top of that data lake. Just the point to note here is that these products integrate very tightly with the data lake. So the data lake has to be one performant, and then also has to expose the API in a very standard and in a very usable format to these developers who are integrating with the data lake. Then there are added complexities of verticals. So we serve at the moment about retail, fashion, hypermarket, food and beverages, quick service restaurants, jewelries, and few other verticals as well. Though the whole reason of having a multi-tenant data lake is there are commonalities between these verticals, right? So essentially, customers come and shop in the stores, and their transactions are captured in some format. While there are commonalities between these verticals, there is also uniqueness within this vertical. So each vertical differs from other verticals in some formats. So the way a marketer in a retail vertical will understand a data lake versus a marketer who's on a hypermarket would differ. So there are nuances that they're different between these verticals, which adds to the complexities. Then comes the size of the customers, and thus comes the expectation as well. So there are super enterprise customers on our platform. There are enterprise customers, and there are thousands of SMB customers as well. Now, when we come to a B2B multi-tenant platform like us, the SMB customers generally would expect the system just to work out of the box. They need to be, working on a very self-serve mode with the products, and probably may not be exploring a lot about, extensibility about the platform and things like that. But they would be interested in getting quickly onboarded onto the platform. While in case of super enterprises, with the other extreme, not only the product has to be performant and should serve all the use cases. There are several tons of users and stakeholders on the super enterprise platforms as well. And the expectation generally ranges from not just having complex features on the product, but also their ability to work on top of the data lake in a flexible format. So that's adds to the complexities of size of the customers. And the combination of these leads to various types of users on the platform. So first is development teams. As I mentioned, we are very tightly integrated. The products are very tightly integrated to the multi-tenant data lakes. Developers need to be able to access those data lakes by not requiring to know very, very details of this data lake. How does the Spark SQL perform, for example? But they would want to access the data lake in a very domain-specific context. And similarly, there are data analysts and data scientists who could be internal, who could be external. And then those data analysts, on the other hand, would be interested because they're working for a particular tenant or a particular brand. they would be interested in looking at what that schema for the tenant looks like, irrespective of the APIs and things like this. And then there are marketing managers who would be running campaigns on our platform. They would want to slice and dice data, and since they would be interacting to the data lake through a targeting platform, the expectation is just like any other page load. So the page load times should be high. Then there are stores and zone managers, zonal managers who would be looking at the data every day in the morning when the store opens. And then there are CXOs who will be looking at, very, very business-centric dashboards on our platform as well. Now, a combination of all these leads to various expectations, and we'll touch upon about 5-6 of them today. The first is developer needs to access the data in a common format, which is essentially a commonality across all the tenants. It should be easy for them to be able to connect to the data lake through a domain-specific language rather than trying to learn about a particular language like a Spark or a Presto and things like this. And analysts should be exposed to their own relevant schema because they're working for a particular tenant. They would want the schema that is very, very relevant for them to be exposed. They don't care about how the multi-tenant system works. Then there are various frequencies of data access. So the data readiness. Some users on the system would want to access different parts of the data throughout the day, and they would have a specific frequency of access the data as well. A marketing manager might be looking at the data once a week, but a store manager or a zone manager might be looking at their data every day, how their store is performing. And that leads to load time expectations where people, the parts of the system that they are accessing, they would want that load time to be faster. I think in the modern data lake concepts, the page load times have almost equivalence of application page load times. And the last point is around data governance and extensibility. Particularly when it comes to super enterprises, the data governance and data extensibility becomes super important because they would want to play around with the data lake and also add their share of domain specific nuances to the data lakes as well. Now, coming to the architecture, the left-hand side that you see is essentially the microservices architectures that we have. So each microservice is responsible for doing a certain type of work, and each microservice can have their own data stores. Primarily, it is MySQL and Mongo for us, but it could be event streams. It could be external facts. The external facts are essentially the entities that we don't capture on our platform, but they could be relevant for the data lake for that tenant. Now, there are various ways to get that data into the data lake, which is Scoop is a standard way. Then there are event streams. There are external locations that you define. It could be on S3 through which you can import the data to the data lake. Now, the grayed out boxes here, the workflow manager and the meta servers are the components that we have built inside Capillary, and I'm going to talk a little more about it in upcoming slides. And the workflow manager is essentially responsible for running this stages, right? So ingest the data, merge the data, link the data, and then generate KPIs and probably then run a lot of scheduled jobs. Scheduled jobs could be send a report out to the customer. It could be refresh a particular segment of the users based on the incremental data, or it could be run a recurring campaign. It could be any of those scheduled jobs. Now, this workflow manager is responsible for running the stages of the data, and finally, everything is built on Spark, Apache Spark, as I mentioned before. And although this workflow refers to the meta server, which is essentially stores all the tenant-specific metadata to generate the stages of the data flow. And finally, it persists that data to S3, and then that. In the subsequent slide, I'll mention how this S3 data lake is used and integrated in the products as well. This is a very standard flow of data flow. The components to note here is the workflow server and the meta server, which I will be elaborating further on my slides. Now, once this data lake is formed, then what do you do about it? So The data lake is persisted on the cloud with S3, which has various resolutions of the data. Could be the raw data, could be the linked data, could be the summarized data, could be the cubes. And that data lake is then exposed through a query interface to our products, which is Insights Plus, Marketing Cloud, our export framework, or our segmentation engine. All of these products interact with through a query server to this Spark cluster. They don't directly fire Spark SQL queries. I'll also elaborate this grayed out box, which is the query server in Capillary's context. Now, there are three parts to it, which is the workflow manager, as I mentioned, during the data pipeline, query server during serving layer, and the meta server, which basically hosts all the tenant-specific metadata. Now, apart from all these four products that I mentioned, there are also uh, products which directly interacts with the data lake, not through the query engine, which is the managed notebook solution, which extends the capabilities of our data lake and extends it to our customers. And then there are AI pipelines, which is moves from validating the data, training, and then inferencing the data as well. And uh, uh, some of these output of this data pipeline again feeds back to the products as well. Like for example, you could take the customers facts, which is transaction, and then process and find out different propensities of user of purchasing for the next 20 days, and then feed that back to the products so that the products can be more intelligent in nature. So this is an iterative AI data pipeline that works on that data lake directly. So having given a context of a little bit about the ETL or the data pipelines and then about the read use cases, let me go through quickly about a few of the screenshots of the product. The first one is Insights Plus product, as I mentioned, is a business intelligence tool, which is essentially for any user, they can create their own charts. They can compare the KPIs across different time segments, or could be across different customer segments and stuff like that. So, and it provides us a library on which you can either use the standard reports out of the box, or you could create your own charts and the reports as well. The thing is here is to note it is that, let's say it's a customer which belongs to a jewelry categories, they would have their own KPIs, and which is will not be visible for a customer, let's say in a hypermarket segment. There's a second product, which is the Engage Plus product, which is primarily the targeting platform for our marketeers, for our customers' marketeers. Here, for example, they're trying to run a campaign in which they would want to include the loyalty customer, filter it by say customers who purchased in the last 5,000, more than last 5,000 in the last 6 months, and probably they would want to put down some AI powered filters, which could be say a transaction prediction. Give me all the users who would be who have transacted in the last 6 months of more than 5,000, and they would have a high propensity of buying in the next 6 months, and we would target them with a new product launch. So that's the use case that would essentially lead to our query server and lead to a query on the data lake and filter out those customers. And to note here is that these are interactive in nature. Then the third product, which is the segments, you could divide the customer segments into various buckets. Again, those buckets are configurable. You could say, this is my active definition. This could be my semi-active definition. This is my inactive definition. This could be an active 2 definition. And this varies from tenant to tenant and vertical to vertical. And you could write different rules to bucket and segment those customers out. Now, what have been our key learnings of building such a platform with a tightly coupled product ecosystem to the data lake, as well as catering to this uniqueness of different tenants across different verticals, and understanding the users, what do they really want from the platform, and how do we power them. Now, first learning for us has been the metadata. I mean, that is probably the biggest and the learning that we had in the last couple of years to how do we model the multi-tenant data lake in the first place. Now, draw a parallel to a single tenant data lake where typically a metastore would contain a Hive metastore, or a Spark metastore would contain schema of the tables that are required. It would contain the location or the physical path of the data lake and stuff like that. But when it comes to a multi-tenant data lake, you couldn't really write all those queries and all that in manually because every tenant has different factors to it. While this slide captures a lot about different aspects of it, I would cover some parts of it. One is scopes. So what are the scope this tenant belongs to? What are the supported verticals? So does it belong to a hypermarket? Does it belong to a QSR? Does it belong to a fashion category? What are those KPIs that are defined on those verticals? What are some of the best practice KPIs that are defined on those for those verticals? Now, when you're modeling data lake, you have to understand the entity relationships. In this case, a tenant could belong to a vertical, or it could actually belong to multiple verticals as well. So it could be a multi-brand retailer, which that supports today, hypermarkets as well as a jewelry brand. They could be more org units inside the tenant, or it could be a multi-brand retailer as well. Now, what are the source tables and the entity relationships? What are the supported source tables that is captured for this tenant? And it could be external data as well, that's very specific to that data lake. Now, at the end of the day, it exposes a bunch of APIs. The APIs are given a fact, given a tenant, tell me all the dimensions, given two facts, tell me all the common dimensions, or load catalog for the tenant, and stuff like that. So, and this tenant metadata is something that is very, very crucial, and it is less related to the data lake, but related to the overall modeling of the system together. And both are workflow manager, which is responsible for the data pipeline, as well as the query engine that is modifies and rewrites query and fires the tenant specific queries. Both use this tenant metadata system for their own development, as well as serving to the next layer. So a part of important learning here is that this is something that comes from the domain understanding. If you're building it for any other domain, you have to model the metadata first before actually building out the data lake. The second learning is around a KPI bloating of KPIs across when you try to build a multi-tenant data lake. So here are some of the customers who are asking things, right? So one of the customers says ABV is average basket value. Exclude plastic bags from my ABV calculation. So I'm a hypermarket. I give out plastic bags in everything that the customer buys, but I just want the ABV calculation to exclude the plastic bags that is there on the bill. But for some other customers, like a fashion, it may not be applicable. Right. So there are various variations in KPI definitions. I want average transaction gold weight to be tracked. This is specifically relevant for jewelry brands. They want to track the average gold transaction weight in a particular transaction. And when you go to, say, an electronics store, a couple of customers, they just say, give me iPhone sales. I don't care about anything else, right? Because that's what has been selling on my platform. So now what it leads to is different types of KPIs and KPI bloats. And how do we handle this? Because if you try to, it could be solved by in our older system, we used to just give out variations of creating those KPIs. Just go ahead and create whatever KPIs that you want for the platform. But the problem that it leads to is KPI is not a final state. It is essentially used subsequently in AI data pipelines, or it could be used by users who are not defining those KPIs. So KPI is constructed in a different way and used in a different way. Now, if the definition of those KPIs bloats over a period of time, it's very difficult to find semantic meaning out of the KPIs. So that's what is super important for me for a platform like us. To capture the semantic meaning and construction of those KPIs. So the semantic meanings could be around what does that KPI indicate? What level it is defined? Is it defined at a user level? It is defined at store level? What scope does it belong to? Does it belong to a global scope, like everybody understands this KPI, or it belongs to a particular vertical, or it belongs to a particular tenant? It's very specific to the tenant. It could be a multi-phased KPI. It could be filtered KPIs. It could be windowed KPIs for a particular time duration, like an average basket value, but particular duration of the time, right? So what we do is that we have a KPI lifecycle management engine, which is essentially configurable. So each KPI is parameterized. They're configurable so that you could tune certain parameters, and the KPI can be adapted for that vertical or for that tenant. A KPI could be overridden. So it follows that you could override that KPI and say that this is my new definition of that KPI. But it primarily indicates the same thing. It talks about average basket value, or it talks about campaign performance, but what I'm doing is calculating this differently. Or it could inherit and then do certain ways, right? So the KPI lifecycle management is super important to address the KPI bloat, and that is relevant because we are building a domain specific data lake which has to understand what this KPI does and can be used by, say, analyst or a data scientist who's not necessarily defining those KPIs upfront. This definition is done by somebody else. The usage is being done by somebody else. And whoever is using it doesn't need to understand how it is being created or what are the finer nuances of calculating those KPIs. The third point that I wanted to discuss is on scheduling and data availability. This is particularly relevant for the data pipeline, which is essentially generating this data lake every day and also incrementing that data every day. Now, what are the things that we hear from our customers? The time is a crucial factor for all of our customers. Now, the store manager says that my store opens at 8 a.m. I need to see all the reports of my store performance in comparison to other stores at 8 a.m. in the morning so that I can plan my day. A marketing manager, on the other hand, might say, my campaigns run for a long duration time. I'm not worried about every day at 8 a.m., but on a weekly Monday at 12 p.m., I have my own planning sessions in which I need to look at the last week's campaign performance, and then I should be able to plan it. I can't, this report can't be delayed from Monday 12 p.m. Then there are, particularly in case of super enterprises, where the enterprises are syncing the data from our data lake to their platform, they would want all KPIs must sync at 9 a.m. in the morning. Now, so the fact to note here is that everybody has different use cases and they're sensitive to the time when they need it. Now, in our case, it leads to all the data flow or the workflow manager essentially on every day generates about 500,000 nodes. Now, how do you schedule those nodes so that they become the business outcomes or the expectations are met? Now, this is a small part of the or that DAG, which is out of this 0.5 million nodes. Think of each DAG could be a tenant specific super graph. So each tenant can obviously run in parallel. So each of these tenants could be one super graph. And with each tenant, there could be multiple stages. So it could be change data merge. It could be KPI generation. Again, KPI generation could be parallel. There could be two KPIs that you can compute in parallel. And then those stages internally have their own DAGs as well. Now, in this one, the red one that you see is the critical path in the system because the store report needs to be getting generated at 8 a.m. in the morning. Hence, the predecessor node, the store fact computation becomes higher priority as well compared to the green ones, which is campaign facts, because campaign is needed probably end of the week. So think of a graph which is the size of a 0.5 million nodes and also has a depth of nodes. How do you schedule those nodes? Now, here are some of the common pitfalls in scheduling such nodes. What I've seen happening. Generally, the approach that people take is that let's have priority, assigned for tenants or tasks. So there's a fixed priority bucket 1 to 5. You just put tenants across to the buckets. Or then when the use case comes that this particular chat or this particular report is or particular job is relevant for this particular tenant, then the priority becomes multi-fold. That becomes tenant and task level combinations. The other mistake that people do, and that leads to basically a sort of priority juggle, right? So people would keep changing these priorities, but that doesn't have any correlation with the data going out in time. The second mistake that people do is assume infinite scalability on the cloud. While the cloud computing is scalable, but no resource is limited, right? No resource is not unlimited, right? So there are times when you won't get the spot instances. You might not get. There are game days where you actually don't get instances at all for running all of them in parallel, right? So, and if you're talking about dependent task graphs, there would be wastages if you just scale without having any control on the scalability parts, particularly on the data pipelines. Now, what do you do here? What we do here is essentially work backwards from when the output is needed. So say, for example, user wants a particular job to be done at particular time at say 8 a.m. in the morning. Then we try to calculate, when does the predecessor of that node needs to be scheduled, so that this report can be sent out on time, and then work backwards on the graph. So this falls into the category of graph scheduling algorithms. We adopt something called as late as possible time, elapsed time of the graph, and then scheduled the graphs or the nodes which the parents have finished their executions. They're free to execute, but execute in the order of their elapsed time, which is lowest. So the nodes that are critical for the eventual meeting of the goal. So the priority here is assigned dynamically, and if, for example, somebody goes and changes this 8 a.m. to 7 a.m. in the morning, the system automatically adjusts itself without anybody to manually intervene this. So you could look this up. This belongs to a set of graph scheduling algorithm called critical path scheduling or list scheduling. And when is the time to scale? So in the whole flow of that execution of the graph, you look at when the nodes are missing the as late as possible time, and just scale up the resources as per needed. So that basically gives a very simple constructs for scaling your systems. Then comes the query engine, which is at the serving layer. Now, what do we hear from our customers here? The campaign. So I'm a marketing manager. I'm only worried about the campaign performance reports that has to load within 10 seconds. I'm only interested about say customer segment drill up and drill down, or store target performance report is super critical for a store manager. So I want to have super good load time for those reports. So the point here to note here is that there are various users who are interested in various parts of the system, and they would want those systems to be very, very performant, right? So what does our query engine do? So the query engine essentially, which is powers all the products, works in between the data lake and the product ecosystem, parses this DSL. So we expose to all the products a domain specific language, and then it parses that DSL, figure out what this query intends, what are the data catalog that it needs to answer that question, rewrites that query in a way that whether that query can be answered the most granular tables, or it can be answered from a more rolled up cubes or summary tables. And then it executes that query onto that, rewrites that query and executes that query, and then caches that results, and also is responsible for doing a predictive warm-up. So it anticipates what are the queries that are going to run today, and then warms up the cache. Now, the point here, or the main design here to look at is, one is domain specific language, of course. The second is to be able to have a iterative way of defining summary tables. So we don't know upfront which customers are going to deal with what type of summary tables. And traditional warehouses just roll up everything, and that is very compute intensive. So what we do is we keep profiling, and we have a strong observability built onto the platform where we keep profiling the queries and find out whether the queries are slow. And if the queries are slow, can we create a summary table out of it? And if the summary table can be created, it could just appends that metadata, and next time in the ETL pipeline, the summary tables get automatically created, and the queries become faster automatically. So having this lazy or iterative way of defining summary tables, and those summary tables could be defined per tenant or per vertical, that helps us keeps the concurrency in check, so that more queries can run in parallel. Then there are various other aspects as well, having synchronized or asynchronous flow on the query executions. Since all the query executions on the read side is pretty much independent of each other, as opposed to the workflow manager, which has a dependence graph. This has more of independent graphs. So this leverages auto scaling very well, and it exposes DSL for the developers to interact with the platform rather than interacting with a Spark SQL or a more lower level constructs. An example DSL, as I was mentioning, could be on our marketing product, which is say include all the loyalty customers, include customers who purchased more than 5,000 in the last 6 months, who have the top 20% of the transaction propensity. So there are people who are among this 20% of likelihood of the users who are likely to buy highest in the next 15 days, and the likelihood is very high. So the point here to note is that this is what the developers of the platform understand. So they just expose or interact with the data lake through a domain specific language. And the part here where we are calculating a transaction propensity is powered by our AI filters, or this is something that interacts with the data lake and then creates those fact tables and puts the data back into the data lake through external facts. And the developers don't need to understand any of these. They're just interacting with the platform through a domain specific language. The last point that I want to talk about is various aspects of data management, which is generally talked a lot about uh, in the modern data lake concepts, and also super important for multi-tenant data lakes, particularly in the case of super enterprises. Data lineage. Data lineage is something that is important for anybody. It is important for the analyst. It is important for the developers to know if a KPI has been computed, if something has been computed, how it has been computed, or how it has been progressing through the journey of the data pipeline. So in our case, the data lineage is depicted by our metadata server, which is internal, right? So that essentially stores. So there are no scripts that translates the data from A to point. They're basically specifications. So by looking at the specification, you could create a complete data lineage from end to end. Data versioning. Now, what do I do if something goes wrong? How do I backtrack problems? If something has gone wrong, say 10 days back, how do we know that? When was the data lake same, right? So, so in this case, what we do is that whenever the incremental data set comes in through the metadata, we just replace the location of that new data rather than going and updating the data sets. So that helps us keep a data versioning, so that anytime we want to go back, we could go back in time and reconstruct the data lake that was in the as is state 10 days back. And then obviously there are expiry of older versions for reducing cost and things like this. Data resolution. This is super important for various stakeholders. When you have various stakeholders in the system, some stakeholders would want to have the access to the raw data because they are actually validating something on the raw data. They could be users who would be just interested in working on the summarized data, and they could be something in between. They could be around on the linked entities. Example of a linked entity is like this. Let's say you have campaign facts, which is your campaign messages are going out, and then you have transactions of users being made. Those are two fact tables which you link so that it is easier for querying for the end user. To note here is that in the raw data is most unadulterated in some sense, but the summarized data actually might lose some aspects of the raw data, but at the same time it could be highly performant. So there are when you have diverse set of stakeholders, include from developers to analysts to end users, you would want to maintain different data resolutions in your data lake all the time. And this goes in really well with the modern data lake concepts, because modern data lake concepts allows a reasonable time interactive querying on very, very large data sets as well. Data validation. Data validation is when you trying to maintain a 250 enterprise customers. Something could go wrong at any point in time. So it is very difficult for anybody to manually ensure that the data lake is same for a particular tenant. So there are a bunch of heuristic that we run on the platform, which is very, very simple checks like, has a table gotten empty today, or if the data is growing very rapidly, or there is a mismatch between if you fire the query onto the raw tables or summary tables for a particular tenant, or if there are data duplicates that have come for some reason for a particular tenant. All those checks and heuristics we keep on building those heuristics so that we can run it at scale and ensure that data is validated to a great extent before it's presented to the end users. Data governance. That is very, very important for when it comes to super enterprises, and particularly in the context of privacy and the rules that are coming in. And UI is primarily, if you're interacting with the data lake with a UI through a UI, it's pretty easy. That is always the best way to govern the data, expose what is necessary, inject implicit filters when you're firing the queries that ensures the data governance. But if you're extending the data outside the platform, which is around the data extensibility, then you need to have a standard way of having a role-based access and things like that. So data extensibility, this is one area which we had neglected in Capillary for a very long time. Our product suite had a very tight integrations with the data lake, but the data lake by itself was not exposed outside for the external developers or external brand users to build on top of it. This is where modern notebook solutions come in handy. What we have done is that we have exposed the raw facts of the data lakes through managed notebook solutions outside, on which they could run their own queries, they could run different algorithms, they could generate certain output and feed it back to the data lake. And the one point to note here is that because we have a metadata server in between, which stores different entity relationship as well, so we have exposed some parts of that metadata as well in normal Spark tables, so that the end user has a complete information about all the facts and the entities to be able to work on top of that data. This is one area that we had neglected for very long in Capillary, but this is one of the areas where it's been rapidly used since we have built this through managed notebook solution, which is out there in the market. That brings into the conclusion to this presentation. There are few thoughts that I would just wanted to quickly go through, walk backwards from the user personas and the requirements. If you're building domain-specific multi-tenant data lake, you have to understand the user personas really well, their requirements, before you can start designing the data lake itself. There are various capabilities of data lake currently present, and they could be leveraged, but it's important to work backwards from the user requirements. Modern commonalities and uniqueness of the tenant. The commonalities helps you define the multi-tenant platform in a minimum specification way. So a responsibility of platform is to address all the commonalities in the minimum specifications. And that's what is commonality is about. The uniqueness is how that each tenant differ from each other. So understanding the commonalities and uniqueness helps you define the data lake really well. Leverage the modern data lake and cloud computing concept. This is a no-brainer. We experimented a lot around paid tools, different other types of data warehousing solution, but this is the most growing area at the moment. And there's so many capabilities which can cater to different types of use cases, including from streaming to batch to interactive analytics. So leverage modern data lake and cloud computing concepts pretty much fits most use cases. Be cognizant about the cloud cost because it can go out of control easily. Data warehouses or data lakes are probably could be a very significant part of cloud computing these days. And the primary thing for us to note here is that what we generally focus on is having compute when it is really necessary, right? So and then have an iterative way of modeling, have very strong observability in the system to understand what part of the computation is getting unused, and maybe move that to a more lazy mode, and more other parts of the system which is used more often, bring them out or have larger computations on top of it. So planning that out is important, because the cost can really go out of control in case of a system like this. And design for extensibility and governance from day one. There are so many privacy rules that are coming in for each country, and also extensibility. No matter how much you build on the product, the customers would always want to do more on top of the data. So design for extensibility and governance from day one, and that's going to power your data lake to the next level. That brings in to the conclusion my topic. Thank you, and thank you Qbul for inviting me for this talk. You could share the session on social media using the Data Lake Summit hashtag. You could interact with other attendees on Slack at Data Lake summit.slack.com, and finally, a big thanks to our team, which is called Essential Insights team inside Capillary Tech, for building this data lake out and helping all of our customers achieve the data-driven applications on top of our platform. Thank you. Thanks a lot.